Here's an example that comes up a lot when you are playing games like a table tennis. You've got two players, A and B, that are playing a game, and A has a likelihood of P of winning any particular round. And they continue playing until one of the players has won by 2. So you keep going until one player is ahead of the other by 2 games. And so the question we're asking, what is the probability that P is the overall winner? And then what is the expected number of games that are played in total? So we're going to use a conditional argument again. And by now you might be used to a certain pattern, which is that a good thing to condition on here is the outcome of the first game. So we'll say y is going to be a variable. It's going to be 0 if A wins the first game, and 1 if B wins the first game, or equivalently if A loses. And so what is true? So the probability that A wins the series, A eventually wins by 2, is the probability that A wins if A has a victory on the first game times the probability of a victory of a victory on the first game for A, plus the probability that A wins if A loses the first round. So let's look at these one by one. Let's look at this example here. If A has just won the first game, then there are 2 possibilities. So if A has just won, then 2 things could happen. A might win the next game, right? And then the series would be over. It would just be two wins. Or what else might happen? B might win the next game, and then the process would restart, right? So what does that look like here? I'm going to copy this formula that's at the bottom of that slide over there. We'll say the probability that A wins, given that y is 0. So A has won the first game. What is that equal to? That's going to be what? There's a probability of P. So remember, this is right now, A has just won the first game. Okay, it's just won the first game. So what's the possibility here? There's a probability P that A just wins outright. All right, because if A wins the next game, then that's 2 in a row and they're done. What is the other possibility? The other possibility is a 1 minus P probability that A loses, and then what happens? Then A has won, and then A lost, so now they're tied up again, which means they're back to where they started, plus 2 games. So 1 minus P times the probability that A wins. Like that. Okay, so that's how that works. And then you can do the same kind of reasoning for the case where A loses. In other words, if y is equal to 1, and that looks like this. If B has just won the first game, then what happens here? Probability that A wins, given that y is equal to 1. What could happen here? Well, there's a 1 minus P probability that B will win the next game. And if that happens, then A couldn't win, because that means B has 2 victories in a row. So it's 1 minus P times 0 plus, and then what's the other thing that could happen? There'd be a probability P that A would win this next game. And that at that point, you'd reset everything. So B wins the first game, A wins the second, you're back to where you started, and then you just have the regular old probability that A wins, like that. Okay, now you put all these together using the law of total probability. You have the probability that A wins. Let's just write the whole thing out. What is that? That's the probability that A wins, given that y is equal to 0, times the probability that y is equal to 0. And then plus the probability that A wins, given that y is equal to 1, times the probability that y is equal to 1. All right, and we've just worked out these expressions here. So what is that? So certainly I should also mention the probability that y is equal to 0, that's P, because y equals 0 means A wins the first round. Y equals 1 is 1 minus P. And then we worked out these expressions up here and here. And you write all these together, you collect them, and you get this expression there for the probability that A wins. And so as you've seen before, you've got probability that A wins on the left side and probability that A wins on the right. which is fine. You just solve for these algebraically as you would always do, and the expression that you get looks like this thing here, p squared on 2p squared minus 2p plus 1. So that's how you study what happens when you win by 2. Let's look at the expectation. We're going to use the law of iterated expectation, and we'll condition on the same thing. Okay, so we'll condition on y again, and it looks like this. So x is the number of games played, and then y is the same that it was before. Y is 0 if A wins, 1 otherwise. And so we would say expected value of x, as usual, is equal to the expected value of x given y. Like that. And so what are the two options here for y? So y is either 0 or 1 with p and 1 minus p. And so that, of course, is just going to be p times the expected value of x given that y is equal to 0. Plus, and then 1 minus p times expected value of x, given that y is equal to 1. Okay, this is just me writing down the same expression that's here at the top like that. So let's see here. So if y is equal to 0, then what's going to happen? So let's say, suppose y is equal to 0. Let's look at this one. Expected value of x, given that y is equal to 0. So that means that A has just won the first game. What is the expected number of games in total? Well, what are the two possibilities here? There's a probability. So again, A has just won the first game. A has just won the first game, and now we're looking at what happens on the second game. Well, with a probability P, A would win the second game too, and the process would be over, and you would have played 2 games. So P times 2. And then what else could happen? The other option is there's a 1 minus p probability that A loses that second game. And now what happens? You're right back where you started with 1 win for each player, but you've already done 2 games. So in this case, you'd have a 1 minus p times the quantity 2 plus expected value of x. Like that. And by the same kind of reasoning, the expected value of x, given that y is equal to 1, is, what's the probability here? Well, there's a 1 minus p probability that B will win the next game. And so there's a 1 minus p probability of that happening. If B wins the next game, that's 2 wins for B in a row. So 1 minus p times 2 plus, and then what's the other thing that could happen? The other one is that A wins, which is probability p. And then what would happen? You'd be back where you started. So 2 plus expected value of x, like that. Okay, and so now I've got everything I need. I've got all these expressions can be plugged in, and if you do that, and again, you work out the tedious algebra, you'll get an expression here for expected value of x, 2 on 2p squared minus 2p plus 1. And so that's how that works. The next example is mostly an exercise in abusive notation. That's what's really going on here. So you've got x, which follows a Poisson distribution, and the mean for that Poisson distribution is capital lambda, and lambda follows an exponential distribution with mean 1. Let's write out some PMFs and PDFs to make sure we keep ourselves aligned here. So we have x follows a Poisson distribution, and so the distribution of that looks like the following. I'd say f of so I'll use f of x to represent the PMF for, or no, I'm not going to use f of x because I use f of lambda here as the PDF for lambda. So instead, I'm going to say that the PDF for x, we'll call that g of x. Okay, g of x is the PMF for x, and that, if you go back to the table and look up the formula for a Poisson distribution, you see that's going to be big lambda to the capital of capital X times e to the minus lambda all divided by x factorial, like that. And then f of lambda, and this is the weird part now, right? Lambda follows an exponential distribution with mean 1. This is notationally, it's a nasty thing, and that's what makes this problem complicated, is that typically we think of lambda as being a parameter passed to an exponential distribution, but here it's actually the variable itself, which is what makes things confusing. And so then f of lambda is e to the power of minus lambda. Why? Because we have a mean of 1 here, and so there should be a hidden 1 multiplier here times a multiplier of 1 over here, which we are not going to touch. Okay, so that's our PMF and our PDF. And having said that, let's now work out the overall PMF for x. So what is the probability that x is equal to n? And so how does this work? It's really only difficult because of the variables. So the probability that x is equal to n is equal to what? You would look at all of the probability of x being equal to n conditioned on the value of lambda, and then you'd multiply that by the PDF for lambda, like that. And if you refer back to the law of total probability, you would be integrating this from 0 to infinity with respect to lambda. Okay, that's how this works. Because remember, we're integrating over lambda here. That's why there's an integral as opposed to a sum. Okay, so let's work that out. So what is that going to be? We plug in the PMF for a Poisson random variable as I did over here. And so what is that? That's going to be lambda to the power of n times e to the minus lambda over n factorial, and multiply that by f of lambda, which is e to the minus lambda, like that. And then from that point, you just work out the integral, and you find that you throw that into Wolfram alpha, you'll get this nice clean closed form expression here, 1 over 2 to the n plus 1. So pretty simple cut and dry example there. Here's another one that is sort of puzzly or a brain teaser. You have n coins available, and you flip them, and all the outcomes are independent. The coins have nothing to do with one another. And the probability of heads on coin I is alpha I. Okay, so these coins have a funny weighting to them where they're not all even. They're all, some of them are more likely to be heads than the others. But we will say for at least one coin, you have a 1/2 probability of being heads. Okay, there is at least one fair coin in this mix amongst all the others. And so we'll ask, what is the probability of an even number of heads showing when you flip all of these things? And I think I'll spoil the surprise a little bit, which is that the probability is 1/2 of an even number of heads, because everything hinges on that one fair coin. And let's work out how you would prove that mathematically, and that goes like this. The way you would attack this problem, not surprisingly, we've identified this one special coin J. So not surprisingly, you condition on that event. So we'll say H and T is the event that coin J is heads or tails, respectively. And so we'll say E is the event that we're interested in. It's the event that there's an even number of heads. So what can we say? The probability of E, the probability of an even number of heads, of course, is the probability of E given that the J coin is heads times the probability that J coin is heads plus the probability of E given that the J coin is tails times the probability that the T coin is tails. Now, of course, either of these is just equal to 1/2. So it's the probability of an even number of heads times the probability of heads plus 1/2 plus 1/2 times the probability of E given T. Okay, and so what are we saying about this? What does this mean? E given H. E given H means the following. I say, what's the probability of an even number of heads given that coin J is heads? So what does that mean? It means that all the other coins, all coins other than J, the number of heads on all of the other coins is odd, right? And then over here, this is E given T is the probability that the number of heads on all other coins is even, right? I'm just saying even number of heads total means you just deduce the number of heads that would have to be present given this information about the jth coin. Okay, so what do we notice here? We notice that these two events, let me do this here, these are completely distinct from one another, right? In fact, they form a partition. Exactly one of those two things can happen. And why is this significant? Well, let's say whatever this probability is, the probability of E given H, let's suppose that's P. Okay, let's just call that P, whatever that number is. Okay, and that's just saying the probability that all the coins other than J are odd. Okay, so you take J aside and you just ask the probability that all those coins are odd, that all of the heads there are odd. But on the other hand, the other question here says what's the probability that all of the values on the other coins are even, which means this thing here is just 1 minus P. All right, so what are we left with? We're left with 1/2 times P, whatever the heck P is, we don't know, it depends on those coins, plus 1/2 times 1 minus P, and that of course is just 1/2 because the P's cancel each other out. So that's the trick that we used here. We actually canceled out those P's to accomplish what we wanted. I could have, if I wanted to, worked out what that expression is as a function of the alpha J's or the alpha I's, right? I could have written some crazy sum over all sorts of things, but I chose not to do that. It didn't actually help me. The last example here involves two players that are playing the most boring game in the world. They have a coin and they're just flipping it. And the winner of this coin is the first person that sees heads. It's an incredibly stupid game. It's an uneven coin, so that it's got probability P of showing heads. And we just want to know what is the probability that the first player wins. Obviously, the first player has an advantage because they're going first. So we want to see how big that advantage is. Before attacking a problem like this one, let's think about some intuition here for a minute. There's something nice about this problem, which is that if you think about it, you can probably make a conclusion about what you expect the answer to look like as you know, for various values of P. And it would be a good idea to pause the video now to ask the following. Is this probability increasing or decreasing? And also, what do we expect to happen as P goes to 0 or as P goes to 1? Okay, so you could pause this video and think about that for a minute. As to the first question, I think we could say, well, this probability is almost certainly increasing because higher values of P mean the first player is more likely to succeed on the first attempt. So I think we could agree that this probability, it really ought to be increasing because you're just helping that first player. What do we expect to see happen as P approaches 0 or 1? I would say as P goes to 1, probably we would agree that this value is likely to approach 1. Okay, because if P is 1, then you're very likely to get a heads on the first attempt. So player 1 is basically guaranteed to win, right? You are literally guaranteed to win if P is equal to 1. If P is equal to 0, on the other hand, you wouldn't expect this value to approach 0. Okay, what happens if P approaches 0? It means you're very unlikely to get heads. Someone will eventually get heads, but it's going to be very unlikely and it'll take a long time. So what does that mean? It means that player 1's advantage is not very significant, right? Imagine you're playing a game where you're rolling 2 dice and you want to see who gets double 6s first, and that's the winner, right? That's a very unlikely event. And so whether you go first or second, yes, it's an advantage, but it's a very, very small one because this event is so unlikely that both of you are going to take lots and lots of attempts. So we would expect as this probability approaches 0 that this probability of A winning is 1/2. So how do we analyze this one? How do we analyze this problem? What we'll do is we'll say E will be the event that player 1 wins. So E will be the event that that player 1 wins. I used to call this person A. I'm not sure why I changed that. And so H or T will be, again, the outcome of the first flip, right? H versus T is the first flip outcome. And so what can we say about this? So again, law of total probability, the probability of E is equal to the probability of E given H times the probability of H plus the probability of E given T times the probability of T. Okay, so what can we say about this? Probability of E given H, of course, that's 1 because it means player 1 got a heads on the first attempt. So that's all well and good. Probability of H is P. It's the probability of getting heads. It's P. E given T, this one we don't know. Okay, we're going to look at this one carefully. This is the tricky one. And probability of T itself, that's just 1 minus P. So all we need to know is this probability of E given T. If we can reason that one out, everything else is completely fine. And the way to think about this one is to say that from player 2's perspective, once player 1 has failed, once player 1 has missed their first, has flipped tails the first time because we're saying E given T, now player 2 looks just like player 1, right? Because player 1 is lost, so now player 2 has the coin, and now everything from the future for player 2 looks just like player 1. So what do I mean by this? Probability of E given T is the probability that player 1 wins given T. So that's 1 minus the probability that player 1 loses given T, which is 1 minus the probability that player 2 wins given T. Okay, and what is the probability that player 2 wins given T? Well, again, as I just said, player 2, once you have the first outcome, the first flip is a T, it means player 1 didn't win on the first attempt. So now player 2 is holding the coin in their hand, and player 2, now everything looks to them just as things did to player 1 a moment ago. And so therefore the probability that player 2 wins given T is just a probability of E. So therefore we have probability of E given T is equal to 1 minus probability of E. And so therefore what do we have altogether? We have the probability of E is equal to, if you just throw in all these terms together, collect all this stuff, it's P plus 1 minus probability of E times 1 minus P. Solve for probability of E and work those out, and you get 1 over 2 minus P. And what do you notice about this expression? Remember I said before to reason about whether this is increasing or decreasing, and what happens as P goes to 0 or 1. So we have probability of E is 1 over 2 minus P. And so let's look at that. So this is indeed, it's increasing in P. And also what happens is P goes to 0. This thing is equal to just 1 over 2, 1/2, as we wanted it to be. And then as P goes to 1, you have 1 over 2 minus 1, which is 1. So this behaves just as we were predicting it to. And that's how that works. So that's all the examples we're going to do involving conditional, all these conditioning arguments.